So how can you compute a physical property like a resistance or a conductance in such a small device? The basic idea is the following. When you put a battery between the two electrodes, essentially what you are doing is to shift in the Fermi levels or the chemical potentials of the left and the right metallic lead. So that creates an imbalance, and you have a portion of electrons from the left electrode that could go through the molecule and go through the Fermi sea of the right electrode, because these states are empty. And what you have to calculate is exactly this current of electrons going from this region of the Fermi sea to the right region of the Fermi sea. How can you compute that? What you do is computing conductance as a scattering problem. You have electrons that come from the left electrode that arrive to the barrier or to the molecule or the constriction. Part of the wave functions becomes reflected back to the bulk of the material of the electrode, but part of the wave function gets transmitted through the barrier and goes into the metallic lead on the right, and that creates a current. So you have some net current going through from the left to the right. And the current can be computed by a very simple formula, which takes into account this transmission matrix, which is the matrix that relates the incoming wave with the outcoming wave on the right, with this T matrix. If you compute the trace of this matrix and as a function of the energy, you have what is called the transmission coefficient. And the current is very simply the transmission coefficient multiplied by the difference in the Fermi levels of the left and right electrodes. In other words, this window from one Fermi level to the next one. Okay, so this is a very simple integral. If you know what is the shape of this transmission energy, which is just a function that you can calculate, you have the current. And with the current, of course, you have the resistance too, if you know the voltage. And this is what is traditionally called the Landauer-Büttiker formulation of conductance in nanosystems as conductance as a scattering. So how can you compute that in a code like TranSIESTA? Well, you could in principle compute the transmission matrix like a scattering problem, but that's really quite complicated, and we do it in a very different way, which is much more efficient and appropriate, which is using Green's functions. And just a very short detour on the Green's functions. You have a system like this one, which is an open system. You have your nanoscale contact through which the current is flowing, and you have a left and a right electrode. The Green function of this material or this system is just energy times the unit matrix minus the Hamiltonian, all the inverse of this matrix. And in this particular case, it will be the inverse of an infinite matrix, because the left and the right electrodes are infinite bulk material. So this matrix will go infinite and will go forever. You have the coupling, the energies here in the central region and the couplings with the right and left region. But then in the right and left region, you have semi-infinite matrices here and here. So that's something that you cannot compute in practice, but there is a very, very nice trick, which is to set everything up only in a region around the center, the contact, the nanoscale constriction. So you take into account only this small section of space, and you assume that on the right and the left, what you are left is with purely bulk electrodes. So here the electronic structure and the Hamiltonian will be the same as the bulk electrode. So you can do that if this contour is deep enough into the bulk of the electrode. And in this particular case, you can see that the Green's function can be computed solving this finite matrix, which has the size of the contact region, of the number of orbitals in the contact region, and all the effect of the right and left electrodes are given by these matrices here, sigma L and sigma R, which are the self-energies of the two right and left electrodes. And this can be computed very easily if you know the bulk functions of the bulk right and left electrodes, which are very easy to compute because, again, is the inverse of the Green's function, of the Hamiltonian in these regions. So that can be done very, very easily and very efficiently. So with this, you can just, by inverting a finite size matrix, which is perfectly doable, you can get the Green's function of the contact region. And from that Green's function, you can get exactly what you need for transport. You can, for instance, compute the transmission matrix, which is going to be just the Green's function in the contact region, multiplied to the left and the right to what is called the coupling matrices, which is just the imaginary part of the self-energies. So again, having the self-energies of the left and right electrodes and the green function of the contact, you can have the current. And that's a very easy thing to compute. You can also compute something which is a bit more difficult to compute, which is the charge density. You are doing density functional theory. So to compute the Hamiltonian, you need to know the charge density in all the atoms on your contact and your electrodes. How you do that is not so trivial, because in this particular case, you have a bias between the two electrodes. So you have two different Fermi levels. So how can you compute the charge density if you have two different Fermi levels? You don't know how to fill the electronic levels, because for that, you need to know up to which level you are filling out. With this trick of the Green's function, you can use what is called non-equilibrium Green's functions, or the Keldy's formalism, that tells you exactly how to do that. If you know the Green's functions and the self-energy, you can compute the density matrix just by filling the states that come from the left electrode with the Fermi level of the left electrode, and the states coming from the right electrode with the Fermi levels of the right electrode. So you have to compute two energy density matrices, which again have to do with the Green's functions of the left and the self-energies of the left and the right. So these are all things that you can calculate if you have the Green's functions. And this is exactly what TranSIESTA does.